This is a tutorial on finding patterns in mathematics. If we were traveling down the highway at a speed of 50 miles per hour, and every hour we wrote down the total distance that we had traveled, well then after the first hour we would find that we had driven 50 miles. After the second hour we drove 100 miles. After the third, 150. After the fourth hour we'd find that we had driven 200 miles. After the fifth hour we would have driven 250 miles. Now if we look at these distance numbers, 50, 100, 150, 200, 250, there is a pattern between them. To go from 50 to 100, we're adding 50. To go from 100 to 150, we're adding 50. Between 150 and 200, that's a jump of 50. And between 200 and 250, that's also a jump of 50. Because these numbers have a pattern between them, and they're listed in order, we would call these numbers a sequence. Now when we have a sequence, we call every term in that sequence A. And then with that A, we usually have a subscript that tells us the place in the sequence that term belongs. So A1 would be the first term in our sequence. And in that case, our first term, that would be 50. Our second term in this sequence is 100. The third term, or A3, would be 150. A4 would be 200, and the fifth term, A5, would be 250. If we had a sixth term, where we wanted to find A6, well, we would just follow the previous pattern of our sequence. We go up 50 every time we find a new term. So if we're at A5, or our fifth term, and that's 250, and we add 50 to that, we should find that the sixth term, if we drove for 6 hours, would be 300. Now frequently when you deal with sequences, you'll see the terminology a to the n. A to the n is the term in this sequence, but we don't know which term in that sequence. N is the position of that term. So if n was 3, then a to the n would be equal to a to the 3. If we had the sequence 3, 9, 27, 81, and 243, well then the third term, or a3, that would be 27. If our n position was 4, that would mean that 4 would be n, which means a to the n would be a4, and in this sequence, a4 is 81. So if I said that I was looking for a to the n when n was 5, that means that a to the n is a5. And in this sequence, a5 is 243. Other common notation that you'll find other than a to the n is a to the n minus 1 or a to the n minus 2. A to the n minus 1 just means that we're subtracting 1 from n. Well again, a to the n is some term in our sequence. So if we have a to the n minus 1, then that just means that n is 1 less, or this is the term before a to the n in the sequence. A to the n minus 2 would be the term 2 terms before a to the n in the sequence. So for example, if we said that n was equal to 3, that means that a to the n would be a3. If n is equal to 3, that means a to the n minus 1 would be a2. A to the n minus 2 would be a1. Well, in this sequence, 3, 9, 27, 81, a3 is 27. So that means a to the n minus 1 would be 9. And a to the n minus 2, well, that's just 3. Now, if a to the n was a different term in our sequence, say n was equal to 4, that means that a to the n then would be 81. a to the n minus 1 is the term before that one, so that would be 27. And a to the n minus 2 is the term before that term, so a n minus 2, that would be 9. All this notation is important because frequently we try to make formulas that describe our sequences. So again, if I have the sequence 3, 9, 27, 81, and 243, well, the pattern here is that each term is multiplied by 3 to get the next term. To get 3 to 9, I multiply by 3. To go from 9 to 27, I multiply by 3. From 27 to 81, again, I multiply by 3, and 81 to 243, I multiply by 3. Now, if 3 is A1, 9 would be A2, 27 would be A3, and so on. That means that I found A2 by taking A1 and multiplying it by 3. I also found A3 by taking A2 and multiplying it by 3. In fact, every term, A4 I get by taking A3 and multiplying it by 3. If I wanted to write a generic equation for every term in this sequence, I would say that a to the n, depending on whatever term n is, that's always equal to 3 times a to the n minus 1. A2 is a to the n. A1 is the term before A2, or a to the n minus 1. So this could be a formula that describes this sequence of numbers. Now there are two different general types of formulas that we can write that describe sequences. The type that we just found, or we just developed, was a recursive formula. Another type of formula that describes a sequence would be an explicit formula. A recursive formula is a formula where a sequence is dependent on the previous term. So each term is dependent on the term before it. For example, a to the n is equal to 2 times a to the n minus 1. Every term in our sequence is equal to 2 times the term before it. So if we ever write a formula that describes a sequence that has previous terms in the formula, then this is a recursive formula. Now, an explicit formula is a little bit different. An explicit formula tells us that each term in our sequence is found by using the number of terms. Think of that as n. So if I have a to the n, the nth term in my sequence, that's equal to 2 to the n minus 1 power. Notice that this isn't an a to the n minus 1 term. This is 2 to the n minus 1 power. N is the power, not a to the n, or a to the n minus 1. This is an exponent, not a subscript. So if you ever see n in the formula, then you're writing an explicit formula. So now let's take some time and practice our ability to identify explicit or recursive formulas. In our first example here, we have an is equal to 2 times an minus 1 plus 3 times an minus 2. This means that every term in our sequence, an, is equal to 2 times the term before it, an minus 1, plus 3 times the term before that, an minus 2. Because this formula includes previous terms in the sequence, that makes this a recursive formula. So look at our next example. Here we have an is equal to 1 plus 2 to the n power. This n power is not a subscript, this is an exponent, which means every term in our sequence is equal to 1 plus 2 times the position of that term. So since this formula includes the position, or n, that makes this an explicit formula. Our next example is an is equal to 13n minus n squared. So every term in our sequence is equal to 13 times the position of that term minus the position of that term squared. So again, because we're including the position, or n, in our formula, this becomes an explicit formula as well. Our last example, an is equal to 4 times an minus 1 plus 5. This means that every term in our sequence is 4 times the term before it plus 5. Since our formula includes previous terms in our sequence, that makes this a recursive formula. So now let's try writing a recursive formula for this sequence. Here we have 50, 47, 44, 41, 38, and 35. So we want to write a formula, and then we're going to use that formula to find our 7th term and our 10th term. Well, to go from 50 to 47, we subtract 3. To go from 47 to 44, we subtract 3. From 44 to 41, we subtract 3. From 41 to 38, we subtract 3. And from 38 to 35, we subtract 3. So we can see our pattern here. Now this is A1 because it's the first term in our sequence. This one would be A2 because this is the second term in our sequence. A3, A4, A5, and A6. Now we're writing a recursive formula, so that means that our formula is going to include previous terms. Well, let's look at A2. A2 is equal to A1 minus 3. Okay, well, let's look at A3. A3 is equal to A2 minus 3. And A4, that's equal to A3 minus 3. So every term in our sequence, say a to the n, or an, that's equal to the previous term. So we would say an minus 1 minus 3. So this is our recursive formula for this sequence. Next, we want to find our 7th term. Well, okay, we're looking for A7. And that means that that's going to be equal to the term before it, so A6 minus 3. Do we know A6? Well, we do. It's 35. So A7 is going to be equal to 35 minus 3. So A7 then is equal to 32. Now let's find A10. Well, okay, A10, that's equal to the previous term, so A9 minus 3. Except I don't know A9. But I can find A9. A9 is equal to the previous term, so A8 minus 3. Well, except I don't know A8 either. So A8 is equal to A7 minus 3. Well, I do know A7. I just found it. That's 32. So if I plug that in, that means A8 is equal to 32 minus 3. So A8 is equal to 29. And if I plug that back in here, I'll find out that A9 is equal to A8. So 29, and then minus 3. So A9 is equal to 26. And that means that A10 is equal to 26 minus 3 because it's A9 minus 3. So A10 is equal to 23. So we found A10, but imagine if we had to find A50. That would be very hard using a recursive formula. So instead, let's talk about explicit formulas. So let's try writing an explicit formula for the sequence 3, 6, 9, 12, and 15. Then let's try to find our 7th term, our 10th term, and our 26th term. Now remember, an explicit formula includes the position, so it's going to have n in it. We have a sequence that's 3, 6, 9, 12, and 15. And to go from 3 to 6, we add 3. And from 6 to 9, we add 3. From 9 to 12, we're going to add 3. And from 12 to 15, we add 3. So we can see the pattern between these numbers. In this case, A2, that's equal to A1, our first term, plus 3. A3, well, that's equal to our second term, which is A2 plus 3. And so on and so forth. If we wanted to find A4, that's equal to A3 plus 3. But these aren't helping us find an explicit formula because none of these formulas have n in them. Well, let's look at this value of A2. This is A1 plus 3. Let's say I took this and I plugged it in for A2. I would find out that A3 is equal to A1 plus 3 and then plus 3 again. If I took this value for A3 and I plugged it in here for A4, I'd find out that A4 is equal to A1 plus 3 and plus 3. We could keep doing this. This is A5. That's equal to A1 plus 3 plus 3 plus 3 and plus 3. So when I was looking for A2, I added 3 one time. When I was looking for A3, I added 3 two times. A4, I end up adding 3 to A1 3 times. When I was looking for A5, I took my first term and I added 3 4 times. This number of times that we're adding 3 is going to give us our n value. Our explicit formula is a to the n is going to be equal to, now A1 is what's common in all of these formulas. So a to the n is going to be equal to A1. But then we're going to add 3, but we're going to add 3 a certain amount of times. We're going to add it n minus 1 amount of times. So if I'm looking for the third term, I would start with my first term, and I would add 3 times n, which in this case is 3, minus 1 times it. So this is A3 is equal to our first term, which is 3, plus 3 times 3 minus 1, so 2. So A3 would be equal to 3 plus 3 times 2, or 6. 3 plus 6 is 9. And A3 is indeed 9. So this is the formula, or our explicit formula, for this sequence. Now if we want to find 7, or the 7th term, we just plug in 7 in for n, and our first term, which is 3, in for A1. So A7 is equal to 3, which is our first term, plus 3 times n, which is 7, minus 1. So A7 would be equal to 3 plus 3 times 6. 3 times 6 is 18. Add 3 and you'll find that A7 is equal to 21. If we want to find a 10 or a 10th term, well, A10 is equal to our first term, which is 3, plus 3 times 10, the position of our term, minus 1. So A10 is equal to 3 plus 3 times 9. 3 times 9 is 27. Add 3, that means our 10th term is equal to 30. Lastly, we want to find our 26th term. So we find A26 is equal to our first term, which again is 3, plus 3 times 26 minus 1, n minus 1. So our 26th term is equal to 3 plus 3 times 25. 3 times 25 is 75. Add 3 and we'll find out that our 26th term is 78. So that is how you write and use explicit formulas for a sequence. So now let's try building another explicit formula for this sequence. Here, our first term is 1, our second term is 2, our third term is 6, fourth term is 24, A5 is 120, and A6 is 720. Now there's not an easy formula to see here, so I'm going to build a recursive formula first. I know that A2 is going to be equal to A1, and then it's either plus 1 or times 2. I'm going to say times 2. So our second term 2 would be our first term 1 multiplied by 2. Our third term, that's equal to our second term times 3 this time. Our fourth term, that's equal to our third term times 4. Our fifth term, that's equal to our fourth term times 5. And I think I see the pattern here. Our sixth term is equal to our fifth term times 6. Now I'm trying to build an explicit formula though, a formula that involves n. So I can just plug in the term number, say 4, into my formula and come up with 24. Well, looking at my recursive formula here, when I'm at my second term, I'm taking my first term and multiplying it by 2. When I have my third term, I'm taking my second term and I'm multiplying it by 3. My fourth term, I'm multiplying my third term by 4. So basically, my recursive formula means that I'm taking my previous term and I'm multiplying it by the number term here, n. So if I was trying to find my sixth term, I would take my previous term and multiply it by n, which would be 6. Now if I plugged all of this in for A5, because remember A5 is equal to A4 times 5, I could say that 6 is equal to A4 times, now n is 6 and I'm multiplying it by 5, so n minus 1 and then times n. If I plugged in all of this for A4, I would have A6 is equal to A3 times 4, which would be n minus 2, and then still times 5, so n minus 1, and then times 6, so times n. Now if I took this all the way down to the first term, I could say that my sixth term is equal to my first term times 2, which would be n minus 4. 6 minus 4 would get us 2. And then times n minus 3, n minus 2, n minus 1, and n. But as my n value gets larger, I'm going to keep adding another term like this inside my explicit formula here. If I had the 20th term, then I would have n minus 18, n minus 17, n minus 16, all the way down. So I need something to describe this changing value in our explicit formula. The thing that I'm going to use to describe that changing value is the factorial symbol. And the factorial symbol is this exclamation point. If I have n factorial, That's equal to n times n minus 1 times n minus 2 times n minus 3, n minus 4, all the way down until you hit 3, 2, and 1. So if I wanted to solve 10 factorial, well, 10 factorial, that's equal to 10 times 9 times 8 times 7 times 6, 5, 4, 3, 2, and 1. If I had 8 factorial, that'd be equal to 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So my previous explicit formula, a to the n, that was equal to our first term times n factorial. Now our first term, that was 1. So really, we could say our explicit formula is just n factorial. So this is the factorial symbol, and sometimes we use it when we're dealing with certain sequences. Another common symbol that you'll see when you deal with sequences is the summation sign. Sometimes we want to add the numbers in our sequence together. When we do that, we call it a series. And when we talk about a series or adding a sequence or all the values of a sequence together, we use this summation notation. Summation notation is basically this sigma sign, this crazy E. And then we have our upper limit of n, how many terms we're going to have, that's our upper limit. And then our lower limit is whatever term we're starting with. Usually, this is 1. And then next to this sigma sign, we put the explicit formula for our sequence. So here we have a series, or the summation of a sequence. This is our explicit formula. Our nth term is always equal to 4n minus 6. What we want is to find all the terms between 1 and 5 for this sequence and add them together. So basically, we're going to plug in every positive integer between 1 and 5 into this formula, and then we're going to add all of those values together. So first we plug in 1, so we'd have 4 times 1 minus 6. And then we would add that to the next value of n, so 4 times 2 minus 6. And then we would add that to the next value of n, so 4 times 3 minus 6. And then again to the next value of n, 4 times 4 minus 6. And then lastly, plus 4 times 5 minus 6. I'm just stepping up my values of n until I hit my upper limit, because that's where I stop. Now, 4 times 1 minus 6 is negative 2. 4 times 2 minus 6 is a positive 2. 4 times 3 is 12, minus 6 is 6. 4 times 4 is 16, minus 6 is 10. 4 times 5 is 20, minus 6 is 14. These are the values of my sequence. This is A1, A2, A3, A4, and A5. What the summation notation means is that we're going to take each one of these and add them together. So negative 2 plus 2, plus 6, plus 10, plus 14. Add all this together, and this summation is equal to 30. Or this series value is equal to 30. Now here we have a sequence, and the sequence values are being added together to plus 5, plus 8, plus 11, plus 14. If I want to write this in summation notation, I need to first come up with the explicit formula for this sequence. Well, A1 is equal to 2, and A2 would be equal to A1 plus 3. A3 would be equal to A2 plus 3. A4 would be equal to A3 plus 3. And that means that just like my first example with an explicit formula, if I keep plugging in these values, that means my explicit formula, or my nth term, which it's sometimes called, is just my first term, A1, and then we're going to add 3, because we keep going up by 3 each term, but the amount of times that we add 3 would be n minus 1. This is just like our first example when we built an explicit formula. Now A1, we know what our first term is equal to. That's 2. So our explicit formula is 2 plus 3 times n minus 1, or if we simplify this a bit, we'll have 3n minus 1. So if I'm trying to write this series in summation notation, I put my big sigma sign, and next to it I put my explicit formula, which would be 3n minus 1. Now remember that this is term 1, 2, 3, 4, and 5, and then this sequence goes on forever. So below my sigma sign here, or my summation sign, I put my first n value, which is 1. And then above it I put my highest n value. But this sequence goes on forever, so I put an infinity up here. So this would be the summation notation for this series, or the addition of this sequence, if you want to think of it that way. Now when we talk about summation signs, or of series, there's some properties you should be aware of. If you have some explicit formula, and it's being multiplied by some number, some constant, well, what ends up happening is that every term in your sequence is also being multiplied by that constant. Which means you could factor out that c. That also means that you can take this c and you can bring it outside of your summation. You can find the summation of your sequence and then just multiply it by c, instead of multiplying every term. Now, if you're taking the summation of two sequences, you can always find the summation of the first sequence and then add it to the summation of the second one. Same thing works for subtraction. You can always just subtract your two summations. Now this last property, this just means that we have some number here other than 1 in the bottom of our summation sign. Lots of times it's easier to find our summation when it starts at 1, but not when it starts at some other value. So if I had the summation of some sequence from 7 to 3, lots of times it's easier to find the summation of this same sequence from 1 to 7, and then just subtract the summation of the same sequence from 3 to 1. So these are the 4 properties of the summation notation that you should be aware of. Now here I'm going to give you some formulas that make finding the summation of certain sequences very easy. If you're looking for the summation of some constant, say the summation from 6 to 1 of the number 4, well, you notice that this number doesn't have any value of I or n in it. Nothing changes, so every term here is just 4, and then our second term would be 4, and our third term would be 4, and our fourth term would be 4. And since we're adding these terms all together, the easy way to find the summation of this sequence would be to just take our constant and multiply it by the number of terms we have, n. Now if we have another summation here I have from I is equal to 1 to n of I. So this would be the same as the summation from, say, 6 to 1 of I. That means that I is equal to 1, and then we're going to add it to I being equal to 2, 3, 4, and so on, 5, and then 6. If you wanted to find the value of this summation very easily, you could use this formula, n times n plus 1 over 2. Now, if I is being squared, you can use the formula n times n plus 1 times 2n plus 1 all over 6. And if I is being cubed, then it's just the same formula as the individual I, but then we square it. So we can use those formulas and our properties of summation series to easily find the summation of different sequences or series. Here I have 2 being multiplied together. So I could write this as the summation from 10 to 3 of n cubed plus the summation from 10 to 3 of 4. Because I have 2 sequences being added together. Now you'll notice that these don't stop at 1 or begin at 1. Our bottom value here is 3. So instead, I'm going to write this as from 10 to 1 of n cubed minus from 3 to 1 of n cubed. And I'm going to do the same thing for the second summation sign here. I'm going to go from 10 to 1 of 4, and then I'm going to subtract from 3 to 1, summing 4. Now the summation of n cubed from 10 to 1, I can use my formula. This is n times n plus 1 over 2 squared. Now in this case, n is our maximum value, so I would just plug in a 10. So I would have 10 times 10 plus 1 all over 2 all squared. And then I would subtract the same thing, but I would plug in a 3 for n into this formula. So minus 3 times 3 plus 1 over 2 squared. And then for my second series here, this is just a constant 4. So remember, I can do 4 times the number of terms. So plus 4 times 10, and then minus 4 times 3. Now 10 plus 1 is 11, times 10 is 110, divided by 2 is 55. So we would have 55 squared minus, now 3 plus 1 is 4, times 3 is 12, divided by 2 is 6, square 6, this is 36. 4 times 10 is plus 40, and 4 times 3 is minus 12. Now 55 squared is 3025, minus 36 plus 40 minus 12. This will all come out to be 3017. So by using these properties and these formulas, you can find the value of the summation instead of actually plugging in 3 and then 4 and then 5 and then 6 and then 7, all the numbers all the way up to 10. So now that we've gone over the properties of summation series, that completes our tutorial on the introduction to sequences and finding patterns in mathematics.